All right, so central limit theorem, this is our section 6.5. Now what this is going to allow us to do is combine the theory from 6.4. We're going to apply that, our sampling distribution idea. Remember that was taking every possible sample, find the statistic for it, put it in a chart, and then averaging all those results together. And we understood the couple things about that the average of the sample proportions equals the population proportion. The average of the sample means equals the population mean. Same thing will happen with our variance. Now we're going to apply this to our central limit theorem, and that's going to allow us to do hypothesis testing in the next couple chapters. So we're getting there. We're almost to the point where statistics will actually take place. We have just made the jump. You might not be super excited about this, but we just made the jump from populations, working with whole populations, which we've done the last 2 chapters, to actually working with samples now. Did you notice the jump? This last section lets you make the jump. We haven't done that before. Now we're going to use samples to represent populations. That's the idea for our section. So we are on 6.5. We're going to be talking about the central limit theorem. However, all the theory for it, all the hard work we did in the last section, now we just have to kind of put it in practice. However, there are some requirements that have to be met in order for you to use this stuff. Here's your requirements. First off, we're going to assume that we're sampling from a population that has some mean and some standard deviation, okay? So, from a population with a mean of mu, whatever it happens to be, and a standard deviation sigma. We don't have to know what they are, we just have to know that they exist. Here's the requirements. Ladies and gentlemen, you're going to have to really, really know these things because the requirements are going to tell you which statistic you can use, which measure you can use for the next few chapters. So the first requirement is this. This is a big one. The first requirement is N. What's N stand for? Okay, yes, N's going to be a number, right? What number is it? You guys have to know these. What's N? What was that? The sample of size N. That's right. So N stands for sample size. This has not changed throughout the whole course. N's got to be greater than 30. N has to be greater than 30, and if it is, here's what you know. This is very, very, very interesting. This is part of the central limit theorem I'm telling you right here. If N's greater than 30, are you listening? It says no matter what the population looks like, no matter what, whether it's uniform distribution, whether it is skewed to the left, skewed to the right, normal, a U-shaped distribution, no matter what the population is, if you take samples of size at over 30, at least 31, if you take samples of size at least 31, so greater than 30, and you find those, you remember how we're doing all the averages for all those samples, every different sample, and you organize those, the distribution will be normal. That's a pretty big statement. It says no matter what your population looks like, the distribution of sample means is definitely going to be normal. Your book actually does a really good job of explaining that. It's on page, let's see, 289. Look at page 289. They take samples, they use a computer to do this, but they take samples of uniform distribution of size, n size 1, and you get, of course, normal. And uniform. And they say n size 10, and you get almost a normal distribution after you find those things and you average them. And then they take size 50, and it's perfectly normal. It's amazing. That happens also with a uniform distribution, any type of skew that you have, a normal distribution. So no matter what type of population you have, if you take a sample size of greater than 30, and you organize every possible sample that you took, find the statistics for each one in a table, it's going to be normally distributed. So if n is greater than 30, the sampling distribution, that's what we talked about last time, of sample means, that's what you're finding is a sample mean, is normally distributed. If n is bigger than 30, if your sample size is more than 30, then once you find all those samples and you take the statistic for each one and you organize them, it will be normally distributed. That's a huge statement. I can tell that you really don't quite get what's happening here. So let me try to do this one more time. All right, remember our class in here, and we said that your ages may or may not be normally distributed, right? Honestly, I don't care if they're normally distributed. If we had like a class of the whole college, right? The whole college was our population. I took samples of at least 30. So basically, a class at a time. So if I took 30 at a time, and I found the average age for each of those classes, and I put them in order, the distribution of ages is going to be normally distributed. That's what I'm saying here. Okay? Not that the ages are normally distributed. I don't even care. What I care about is that for each possible sample, if I go organize that data, it's going to be a normal bell-shaped curve. Are you with me on that? That's what this is saying. Not only this, but do you remember from last time, this was the whole theory part of it, that when you took the average of the sample means, so basically the average of the averages, that was the last thing we did, that it actually equaled the population mean? Do you remember that? When I averaged the sample means. When I averaged the sample means. I'm using this symbol because I'm taking all the possible sample means. That's why it's mu. Stick with me up here, guys. I can tell some of you are zoning out already. You can't afford to zone out in this section. This is the biggest one we've covered yet in this class. Okay? Everything else was getting to this point. This symbol means everything, right? It means the population. So this is taking every single sample mean and averaging it. That's what we did on the last example from 6.4. If you weren't here, you need to go and review that video. We took every possible sample of size 2 in that case. Do you remember that? We found the average for each one, then we averaged those. This is averaging all the sample means in the sampling distribution, and we found out that this actually equals the population mean. The average of the sample means must equal the population mean. Now there was one more thing that we really didn't talk about standard deviation, because standard deviation, there's a little bit of a problem. The standard deviation of the sample means is not going to be the standard deviation of the entire population. Now here's why. Here's why. When you find a sample, right, you're taking a pretty large group of people, and if you put them in order, they're going to make it pretty close to the mean. It's going to kind of squeeze everyone together, because you're taking people with really high ages, maybe really low ages, and you're combining them by averaging them, right, with other people who are around that probably average age for the college. It's going to mash some values together. If I find the standard deviation, or the difference between those things, the average distance amongst values, it's going to be less than the population as a whole. What I'm saying is this. If I took all of your ages, we have some older people in this class, we have some younger people in this class, right? There's going to be quite a spread there. Do you agree? There's going to be a pretty good standard deviation, whatever it is. Maybe it's 3.2 years is your standard deviation. I'm making that up off the top of my head, or otherwise I'm just a genius and I can do it like that. That'd be awesome. But now imagine this. If I take all of your samples of size 5, remember the size 5 thing? No, that's not even a size 30, that's a size 5, but you're going to get the picture here. If I take you 5 people and I average your ages, and I take you 5 people and I average your ages, and then I take another mix of 5 people and average their ages, I do that for every combination of 5 people, what's the difference between the averages of those ages? It's not going to be 3.2. It's going to be a lot less than that. Because when I average out your group of 5 ages, I lose those people who are way old. I lose those people who are way young. I've now averaged you together. Does that make sense? So the standard deviation actually becomes smaller. There's less of a spread. Here's what this says. There's less of a spread amongst the averages than there is amongst the data values. When I take samples of size 30 especially, there's going to be less of a discrepancy or a distance or an average distance amongst those averages than there is amongst the whole population in general. Do you see the point here? So this doesn't happen. The standard deviation of the sample means is not equal to the standard deviation of the population. Standard deviation of the sample means. What this says is you take every single possible sample, you find its average, and then you found the standard deviation amongst those. That's what that's saying. That would be the groups of, here, I know we're using 5 instead of 30, but so you can kind of grasp it. If I took all the groups of 5 in this class, all the possible combinations of groups of 5, found every one of your average ages, put them in a table, all 80,000, whatever there was from last time, and then I found the standard deviation amongst those averages, that's this. It is not going to equal the standard deviation of the class. It's not going to be the same. It's going to be smaller. In fact, it's going to be the standard deviation of the class divided by the square root of your sample size. That's actually significantly smaller. What this says is that the standard deviation between your sample means is actually based on the size of the sample you take. Hope that makes sense. Let's think about this mathematically. Okay, you made it through Math C, right? You're above. Some of you are above calculus. But what happens when I divide by a larger number? What happens to the fraction as a whole? It gets bigger or smaller? I divide by a bigger number, the fraction as a whole gets. You divide by 10, or you divide by 100. The divided by 100 makes it a lot smaller, right? This is what's happening. If I take a bigger sample size, I hope you can see the theory here. If I take a bigger sample size, the spread amongst my averages is smaller. If I take bigger groups of you, then I average you, you're going to be even closer together, speaking of averages. Does that make sense? So as my sample size goes up, my standard deviation for my sample averages goes down, gets closer. The distances between those averages get smaller and smaller and smaller. The deviations come together. How people feel okay about what we're talking about so far? So there's a couple magic numbers here. The first one, one magic number actually, is 30. If your n is greater than 30, and you don't know anything about your population, doesn't matter. You know for a fact the distribution of sample means is going to be normally distributed. That's huge, huge statement. You don't need to know anything about your population to make this case. You just say, hey, my sample size is large enough. I know my sample size is large enough, and if it is, that's going to happen. If it is, that's going to happen. That's kind of cool, right? If my n is greater than 30, I know that the average of my sample means will equal the average of the population. I know my standard deviation of the sample means will equal the standard deviation of the population divided by the square root of n that's based on the sample size. Now there is another case. What happens if, what's n mean again? Good, all right. What happens if that happens? Can I make these cases? And the answer is, what do you think? Not in general. If n is greater than 30, here's what's kind of nice. What's really nice. What's very important for you. If n is greater than 30, I told you this is going to be an automatic truth. No matter what your population looks like, this will happen. Nudge you if you agree, or if you're with me on that. No matter what, if that happens, this stuff happens. You got it? If this doesn't happen, we have to make another claim. We have to make another claim. You have to actually say something about the population. You see, here I said nothing about the population at all. I didn't tell you where it came from, did I? I said you're just sampling from a group of people. Who cares? It could be a U shape. That's the opposite of a normal distribution. Could look like that. Yet this is going to happen. The sampling distribution will be normal. Now, if I tell you this, I've got to say something about the population to make this stuff work. I've got to tell you that for this stuff to work, if your sample size is less than 30, your sample has to come from a population that is normally distributed. You with me? It's got to be normally distributed. If you're sampling from a normal distribution, the sampling distribution of sample means will still be normally distributed. If the population is normal, it should make sense that the samples are going to be normal when put in a distribution. Do you follow that logic? If the population is already normal, I take samples, no matter what the sample size is, organize them in the chart after I find each of those statistics, you're going to get a nice bell-shaped curve again, if it's coming from a normally distributed population. If the sample size is greater than 30, it doesn't matter. If it's less than 30, you have to have that statement. So, if n is less than or equal to 30, and I tell you specifically the population is normally distributed. Here's what's true. The sampling distribution of sample means will also be normally distributed. Then the sampling distribution of sample means is also normally distributed, and the same stuff will hold. It says the average of all those sample means, even though the sample size isn't more than 30, it came from a population that's normally distributed. The average of all those sample means is going to equal the population mean, and again, the standard deviation of those sample means will equal the standard deviation of the population divided by the square root of n. It'll still hold. Same exact knowledge. You guys see it? Look at the board with me. Do you guys see that this is the same exact statement, except that one more thing has to happen here? Look at the board with me. Follow me along before you start writing this. If n's bigger than 30, no problem whatsoever. You don't even have to read more on the problem. You know this stuff is going to work. Nudge your head if you're okay with that. If n's less than or equal to 30, you have to keep reading. If it says population is normally distributed, can you do this stuff? Yes. No problem. No problem. Then everything works. Same exact stuff. Nothing's going to change here, whether you have a sample size bigger than 30 or less than 30. The difference is, if it's bigger than 30, everything works no matter what the population looks like. If it's less than or equal to 30, it does matter what the population looks like. It's got to be normally distributed for this stuff to work. Are you okay with that? Have you thought of the last case? There's a case 3. What's the case 3? I've had n bigger than 30, everything works. I've had n less than or equal to 30, but we have a condition. What's the last case, do you think? What? Okay. I've heard lots of no. I don't know. I'm going to move my mouth so you can't really hear me. Yeah, what happens if n is less than or equal to 30? And you know nothing about your population. Specifically about the distribution of your population. Notice that these are the only three cases you can have. This is it. You either have n's bigger than 30 or n's less than 30. If n's bigger than 30, no problems. No worries, mate. You got this. That's Australian, by the way. Did you like my accent? N's bigger than 30, no problem. You got this. If n's less or equal to 30, you have two cases. One, if the population is normally distributed, no problem. Again, you got this. If the population is not normally distributed or you don't know anything about the population, this is actually going to be your favorite one. You know why? You can't do it. Please give me 10 of those on the test. You can't do it yet. Okay, maybe not 10 of those on the test anymore. Yeah, this is why you have to understand this stuff. Okay, because it's gonna happen a lot. You're gonna have to tell the difference between something called a z-score, you know what z-score is, and a t-score. You don't know what t-score is. And it depends on the difference between these two cases. If n's greater than 30, you use this stuff. This is great. If n's less than or equal to 30, you have to choose between these. Right now, you can't even do this one. So right now, you live in these two worlds. N's greater than 30, great. N's less than or equal to 30, check the distribution. If it's normal for the population, okay. If it's not, you can't do it right now. How many people understood what we talked about so far today? Good, that was a whole lot of talking. I hope you understood it. If you're not, now's the time for questions. You guys have any of those questions? You look so sad. This is funny. This right here, this whole stuff, this is the central limit theorem. Okay, this is it. It says that if a population's random variable x, so if your x has a mean of mu and a standard deviation of that, it just means that a mean exists and a standard deviation exists somewhere. The distribution of our sample means is going to be normally distributed, and this is going to take place. The average of our sample means and the standard deviation of our sample means is going to equal the population mean and the population standard deviation over the square root of our sample size respectively. That's going to happen if n's greater than 30. That is the central limit theorem. Okay. It also continues to go on and say if that doesn't take place and you know the population is normal, this is still true. Same exact information. It also continues to say if it doesn't, well, you fail these two cases then, and you can't use this section. Just a couple little notes on the notation. This right here, just so you can read through this again and kind of understand what we're doing. The average of sample means. The average of sample means. Sample mean, what was the symbol for sample mean that we had? What was that, Jan? What was the average? What was the sample means? What's the symbol that we have for that? Just the sample mean itself. When we do the sample mean, beginning of class, first chapter, just x bar. If we take the average of all of our sample means, and average looks like that, that's how we're getting ux bar, okay? So when you see this is the average of sample means. That's what that means. That's what I've already explained it to you. I just want to make sure you see it again, so you have that. The standard deviation of sample means. Again, sample means is x bar. Standard deviation is canon, sigma. Yeah. The standard deviation of sample means, that's this one. This says the standard deviation of your sample means. That's where those symbols are coming from. Kind of tells you what they are. Standard deviation of sample means, we know it's this thing. Mean of our sample means, we know it's that thing. By the way, this that's always true. We always have that. And this is also true. This, by the way, is often called the standard error. So if you ever hear of the standard error, if your homework problem asks you, find the standard error, this is what it means, okay? That's the standard error. Also called the standard error. How many people feel they understand this stuff and are ready to move on to the next little segment, make a jump? Do you understand the stuff before we make the jump? For me to jump into hyperspace. Star Wars, anybody? Did you get this? Hyperspace is Star Trek? Man, I'm not dorky enough yet. Darn it. I gotta really learn my space.
Isn't it both?
Yes.
I don't know. I thought warp drive was Star Trek, but you know. I don't know. All right.
Find out later.
Okay, Han Solo, here we go. Wait, no, it's Captain Kirk. Whatever. Beam me up, Scotty. Let's continue. Did you get this? Greater than 30, no problem. This, less than 30, if it's normally distributed, no problem. This, can't do it. This is our notation. Let's make the jump. In the previous sections, well, besides 6.4, where you really did no actual mathematics, in the previous section before that, 6.2 and 6.3, what we did is we found the z-score for individual pieces of data. What was the z-score for an individual piece of data? How do you find it? You tell me the formula, you should have it memorized by now. You should have it memorized by now. Good. Or in other words, x minus mu over that sigma. Yes? Hopefully you know that. You've been doing that for a while. This was for an individual data value, for an x. For an individual data value, that's our x. What this section allows you to do is to take a sample and work with a sample. You see, the problem is this, folks. You ready for the problem in statistics? The problem in statistics is in order to find a z-score and be able to use a standard normal distribution, which is the only reason why you ever find a z-score, is to use a standard normal distribution. Remember that the table you've been working with? It's a standard normal distribution, yeah? The only reason why you do that is to work with it. But in order to compare a single data value, you have to know this and you have to know that. That's the problem, right? You have to know those things for your population. So if you take a sample, it wouldn't really matter. You'd still have to know the mean and the standard deviation for the whole population to place that one value on that standard normal distribution. Now we're going to make a jump and say, hey, we don't just have one value. I'm not just sampling one person out of my group. I'm taking a full sample size, right? In that full sample size, I'm going to find the average and the standard deviation. Here's what the jump lets us do. What all this theory boils down to pretty much. Instead of an individual data value, I don't have those anymore. What I have now is the mean of my sample. In other words, instead of x, I'm not dealing with x. I'm dealing with x bar. Instead of, please watch carefully, I'm going to make a transition here in just a moment. I'll automatically translating this into my sample stuff, right? And then I'm going to make a transition from here in just a moment. So first, instead of x, I'm dealing with my sample means. Not an individual, but a group of data. Instead of mu, I'm dealing with my average of my sample means. Instead of sigma, I'm dealing with my standard deviation of sample means. Are you guys okay with the transition here? So instead of individual data values, we're dealing with an average of our sample. Instead of a population mean, I'm dealing with a mean of all of my samples. Instead of dealing with a standard deviation of my population, I'm dealing with a standard deviation of all of my samples. Do you follow me up here so far? Here's the problem. This implies that you have every single possible daily sample, and you found the average for each one, and then you average those. Remember, those are huge numbers of items. And it says the same thing for standard deviation. Fortunately for us, we know a couple things about this. Here's the transition, the part, you're not going to use this the way it is. You're going to use it after we translate it. How much is mu of x bar actually equal to? Mu. X bar is going to stay the same. We know how to find that. This is the same thing as mu. How much is this actually equal to? Sigma over the square root. This right here is what we'll do to find the z-score of a group of data, of our sample. So this was for an individual data value. This is for a group of data values, or in other words, a sample. For an average of a group of values. In other words, sample. That's how you make a transition between an individual and a sample. Now, a curiosity might arise in you. It's a very fancy way of saying you might question, probably wondering, well, Mr. Leonard, I thought the whole idea was to kind of get away from that and get away from that. How are we supposed to do that? Well, we can't. We're going to have to make some assumptions out of this. We're going to have to make some assumptions about the population mean and the population standard deviation. We're going to do that. Fortunately, I'll show you how to do that in the next few sections, okay? So right now, yeah, we're going to have to assume what the population mean is and what the population standard deviation is in order to use this stuff. In the future, we won't have to do that. In the future, we'll be able to go through and not only limit our error, but use our sample itself to make determinations about our population. But we're not there yet. This is just the first little step. How people feel okay about the first little step? So when you're dealing with a z-score of an individual, this one, no problem. We're dealing with a z-score of a group, of a mean, of a sample. This one, that's what we're talking about. Are you ready to try to put this into some practice? You sure? Okay. I'm going to give you two examples. Really, you only need two examples to see the difference here. I'm going to give you two examples that illustrate the difference in what we're doing. One you've already done, one you haven't done yet. Okay, so one is like old stuff. We're going to compare that to the new stuff. So write down both examples, and then we'll do them together. So example number one, and down here example number two. A population of men have a mean of 172 pounds and a standard deviation of 10 pounds. Do you notice something already? Do you notice how we're making an assumption about the mean and the standard deviation of a group of men? Notice? It's in a population, group of men. But we've done a problem like that before. Doesn't it look familiar to some of your homework that you've done already? So we've been doing that this whole time, making assumptions about those things. So population of men have a a mean of 172 pounds and a standard deviation of 10 pounds. Of course, I mean the weight of. I didn't put weight, but hopefully you understand that pounds is weight. What's lubs? I don't know what lubs is. We're talking about weight. Find the probability that a randomly selected man will weigh more than, say, 185 pounds. You know what, let's change it. Let's do 175 pounds. You okay with that so far? You sure? You're sure? Does it look familiar? Done stuff like that before? Let's read the question one more time. The population of men has a mean of 172 pounds and a standard deviation of 10 pounds. Great, no problem. Find the probability that a random selected man will have a weight, or sorry, the random selected man will weigh more than 175 pounds. The first thing you do is translate that to a z-score, correct? Then you draw a picture of it. You'd shade the appropriate side of your standard deviation, or standard normal curve, and then you would find the area associated with that, and that would be a probability. You follow? Now you just need to know which z-score you're going to do. This one or this one. Don't answer that yet. We're comparing to our next example before we do this. Example 2. Same information. A population of men, blah, 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 has a mean of 172 pounds and a standard deviation of 10 pounds. Your problems are going to start off exactly the same. Exactly the same. Same exact wording. A population of men will have a mean of 170 pounds, standard deviation of 10. A population of men will have a mean of 170 pounds, standard deviation of 10. The next part's going to be different. Find the probability, and I hope you see the key words here that I'm about to write. Find the probability that a group of 20 men will have an average weight of more than 175 pounds. Assume weight is normally distributed. We've already read this one pretty well through. Let's read this one. A population of men has a mean of 172 pounds and a standard deviation of 10 pounds. Find the probability that a group of 20 men will have an average weight of more than 175 pounds. Assume that weight is normally distributed. What's the difference between this problem that you've already done in this class and this problem that you haven't done yet in this class? What are they talking about? Is this talking about an individual or a group?
Individual.
Is this talking about an individual or a group? Is this a single data value or an average? Single data value or an average? Notice even the wording, it's kind of given to you, right? If you try to, listen, if you try to plug this into this formula, there's no average to plug in for your sample. There's no n to plug in for your sample. You have an n of 20 here. Do you guys see the n of 20? You have a sample size of 20. Where would you put that? You wouldn't put that anywhere. It wouldn't even fit. You'd be like, where's 20 go? Just forget about it. Right? That's not going to work. Right? Here, do you have a place for the sample mean? That's a sample mean. That's an average of your group of 25 men. You're checking that. Do you have a place for your n? Yeah. Yeah, get a place for everything here. One, you have no sample mean. That says you're dealing with an individual. One, you have no group of whatever, group of 20, group of 40, whatever. You don't have that. That's this. It's an individual. If you have a group, you better have a number for that group. That's telling you, that's saying, please pick me. Pick me. Okay, that's that. Do you guys see the difference in the wording in these problems? Now, the process is going to be identical, which is kind of nice because you've already done it. You're going to find the z-score using one of those two formulas. You're going to draw a picture. You're going to put that z-score on, not the kitty cat, right? Draw it. Standard normal. Put that z-score on the picture, shade a certain side, then look it up. Look up the area. You guys ready to try it? Sure. Okay. So again, number one, we're dealing with an individual or a group. A data value or an average. This is for data values. So we would have this. We'd have first thing, translate to a z-score. What is my x value here, ladies and gentlemen?
75.
Good, that comes first. Minus the mean for the population, how much is that?
173.
Over the standard deviation for the population, what are we assuming that's to be?
10.
This is going to be 3 over 10 or 0.33. You with me, ladies and gentlemen? Let's draw our picture now. Are you getting better at your pictures?
No.
Do they still look like all? Hey, ladies and gentlemen, what number is in the middle of my picture? Hey, is your probability, you know what, some people are still getting tripped up on this. Is your probability 33%? No, what is the 30, what is 0.33? What did you just find? Is that a probability or a z-score? So you've yet to even look up an area. Where's the 0.33 go, left or right? But just slightly to the right. You don't have to be exactly accurate. I'm going to put 0.33 just so we're clear. 0.33. Now, read the question carefully. Find the probability that a random selected man will weigh more than. Are you going to shade to the left or the right? What do you think? Now, I've asked you to either bring your calculator or table. Actually, I asked everyone to bring their table to class. That's code word for get your darn tables out. Hey, tell me something. I've graded your homework, actually. I haven't handed it back to you because I'm putting my grade book, but I've noticed a lot of people make a mistake on this type of problem, specifically on this type of problem. A lot of people are looking up 0.33, which you all should be doing on your z-score, on your table. You're all looking up 0.33. You with me? Now, the problem is this. Go ahead and do that. Look up 0.33. What's your area? Look up 0.33. What's your area?
6293.
6293. How many people found 6293? Left side of the room, did you find it on your table? Okay, now watch. Watch. If you look up 0.33, you do find 0.6293, correct? Correct? The question is, what side did you just find? Did you find the right side or the left side? Your table will only give you the left side. You have to be smarter than your table. If you look at 0.33, it's always going to give you the left, whether you want it or not. I don't want the left, I want the right. How do I take this value and make it the right side, the correct side? Go 1 minus that. That's going to give you this one. So this was 0.6293. I don't want that. I don't care about that. I want this one. 1 minus that is 0.3707. How many were able to follow me on that? Good, that's what you've done before. So this answer is, what's the probability you're going to take a randomly selected person out of this group? Listen to me, you need to know interpretation. What's the probability you're going to go to this population of men, wherever it happens to be, randomly select one guy, and he's going to weigh more than 175 pounds? What's the probability?
37.
So this answer is 37.07%. Now we're going to do one thing with this, and then we'll finish this on up at a later time. But I want to find the z-score and look at the differences here. You're going to now see the difference between dealing with a group and an individual. An individual will be much more spread out. A group, this is going to be comparing this average with all other possible averages. That's what's going to happen here. So we take a z-score. Now, we're working with an average, so what's the average we're checking, ladies and gentlemen? What's our average here for the sample?
175.
Yeah, 175. Now we're not dealing with 175 as an individual's weight. We're dealing with the average of a group of 20 people's weight. By the way, oh, wait. What's our sample size? Oh. What's the magic number? Can I do this? Wait, some people are going yes, some people are going no. Oh, okay. If this statement wasn't here, could I do the problem? No. Okay, you're catching on. Minus, did the average for the population change? 172. So far it looks identical. On the bottom, are we going to divide by 10 or are we going to divide by something other than 10? I know that the standard deviation is 10, but I need to divide that number by the square root. What's the square root of what?
20.
That's our sample size, 20. We're using this formula right here. Now you got to do the standard deviation before you do the division. I'm sorry, the square root before you do the division. What's the square root of 20? 4.472. By the way, don't round that if possible. What you're going to get is 3 over 10 divided by 4. What was it again? 472. Take 10 divided by 4.472. Remember, the more you round, the more you're going to be off. So try not to round this at all. What's it going to give you if you do 10 divided by 4.472?
2.236.
And lastly, give me that. 3 divided by 2.236.
1.34.
That one you can round because of the z-score. Round to 2 decimal places. Did the z-score end up being the same? Look at this. Look at the board, and we'll end here. Notice how this z-score was 0.33. That was pretty close to the average. That means you get a pretty good probability of finding someone who weighs more than that. This z-score, since we're talking about a group, it's much more rare to have something away from the mean. That's why that's what the z-score says. It says that group is further away from what it should be. The group should be pretty close to all the other groups. This is a rare group of men. Awesome. We're going to go ahead and find that the probability is going to be much smaller than that when we look it up next time on our table. Okay? Try that when you go home. Draw this picture, make the z-score 1.34, and find the probability of getting an area greater than that, or the group of men greater than that. So let's continue. So we're looking at these two examples and we're comparing them. The first example was the weight of a single individual, the 175 pounds. We're finding out the probability of randomly selecting one male out of this population, and they will weigh more than 175 pounds. So the idea was we use the z-score x minus mu over sigma, because we're dealing with one individual guy. That was our x value. That was our continuous random variable. We found out that z-score used, well, the 0.33. By using this formula, we put that on our chart. Why did we shade the right-hand side of that, by the way?
Because it was more than.
We're looking for greater than, so we want to the right of that. Remember that what you're doing here is you're translating the weight of 175 pounds into a z-score so that you can use your table. That was the whole idea. I've been trying to get that in your head of what we're doing this whole time. Are you guys with me on that? Okay. So the probability, when you look that up, you got 0.6293. Of course, this is always giving you the area to the left of whatever z-score you're looking up. You got to be smarter than the problem. You got to draw your pictures appropriately. We know in order to get the correct area, we're going to take 1 minus that value. That gave us a probability of 0.3707, or in other words, there's a 37.07% chance that you're going to go to this population, you're going to randomly select an individual, and they'll have a weight of more than 175 pounds. Raise your hand if you're okay with interpretation. So about a 37% chance. You're going to go to the population, pick a guy out, he's going to weigh more than 175. You got it? Now, the next example is a little different. The next example said, suppose you had a group of 20 men. Suppose this population is normally distributed. What's the probability that the average weight for those 20 men will be more than 175? Here's why this is going to be more rare. Because we're going to find the area in a minute. It's going to be way less than 37. Here's why this is more rare. Is it more rare to find one person weighing a whole lot, or a whole group of people weighing a whole lot more than the mean? Well, it's more rare to find a whole group of people weighing more than the mean. Because one person, yeah, they could be an outlier. But as soon as you take a whole bunch of people and you average their weights, that average is going to tend to be close to the population average. And also, the bigger sample size you get, the closer it's going to be to the population average. Are you with me on that? So when we start to deal with groups of people here, not just individuals, it's going to be more rare to find out, like in our situation, that an average of 20 people is going to be more than a certain weight compared to the probability of one person being more than a certain weight. So in our case, we did the formula for z-score, x bar minus mu divided by sigma over the square root of n. And this gave us our z-score of 1.34. Already you can see that this z-score is further away from our central score of 0. It's further away than that. We'll still put this on our chart, so we have z equals 1.34. And again, the question asked, what's the probability that these 20 men, the average weight of these 20 men will be greater than 175 pounds? Remember again, look at the board here real quick. What we're still doing, we're still translating this 175 into a z-score. Only this time, because it's an average, because we're dealing with a group, it's a larger z-score. It's saying it's further away. It's more rare. So we still put this accordingly on our standard normal distribution, and we're still looking for the average weight to be more than what this is. Remember, this stands for 175 pounds. That's what this stands for. We're still looking for the more than. So you should all have your tables. Right now I want you to look up the z-score of 1.34. Or if you'd like to use your calculator, you need to be proficient with both. Use your table right now, or if you'd like to use your calculator, what you'd be plugging in is 1.34 to what number over here? To 10. Yeah, because that's where it doesn't actually stop, but that's large enough for us. So you're looking at 1.34, 1.3. How much is 1.34? What now? 90, 99? 90, 99? Okay, got it. Wait a minute, so 0.9099?
Yes.
Like that?
Yes.
That?
No.
Wait a second, what happened? I pointed to here. Is that right?
No.
Where is 0.9099? Is that this area?
No.
That's not the area I'm looking for. That's this area. So you need to know that the area is always going to be to the left. That's what the table is giving you. It's actually giving you this. That's 0.9099. Okay, so how do I find this area if my table only gives me the area to the left? I subtract it from 1 because I know the whole area is equal to 1. So our area, our probability is point what?
0.9.
Raise your hand if you're okay with the mathematics. Now I want you to listen to the interpretation. Here's your interpretation for this thing. The interpretation, I'm going to write it out for you, is the probability of randomly selecting a group of 20 men whose average weight is more than 175 pounds is approximately 9.01%. Is there a difference between these two problems? There's a pretty big difference. This one, here's the interpretation. I'm not going to write that one out because we've done that problem already. Here's the interpretation for this. This one says the probability, hope you're listening, hope you're watching up here, the probability of randomly selecting a man whose weight is more than 175 pounds is equal to about 37%. The probability of selecting a man, a single person. This one says the probability of selecting, if you remember the question from last time, the probability of selecting a group of 20 men whose average weight is more than 175 pounds is 9%. Why did it drop so much? That's not rhetorical. Why did it drop?
To find a whole group is more rare.
Yeah, to find a whole group of people randomly who weighs more than average is more rare than finding an individual. For instance, I gave this example last time in class. I said, let's say we were talking about, I don't know, height or something. Let's talk about height. If I said, if I random selected one of you people, and what's the probability you're going to be more than 5'6"? Well, probably pretty good. There's lots of you more than 5'6", right? But if I said, select a group of 15. Now, what's the probability that the average height of that group of 15 is going to be more than 5'6"? Well, I don't know. Because once I average people, I have people who are tall and people who are short, right? That's going to push you all towards a central average. That means that the probability that the average is going to be more than that height is more rare than finding one person who's more than that height. Are you with me on that? So finding a group of people who's more or less than a certain value is more rare than finding an individual for that same value. Raise your hand if you feel okay with our example so far. Good, that's fantastic. That's everybody. Now, why do we do this? Why is this even important for us? Well, there's one little step we have to do for the rest of chapter 6. One little thing, and then we can start getting into something called confidence intervals, and that will ultimately lead to hypothesis testing. But here's the basis for hypothesis testing. It's called the rare event rule. Do you guys know what a hypothesis is? What is a hypothesis? You've had science classes before, right?
Educated guess.
An educated guess. Or in other words, it's a statement that you're trying to prove true or false. That's really what you ultimately try to do in science, right? You have this statement and then you see if your experiment verifies that statement or proves it wrong. That's exactly what we're going to be doing in this class, only with mathematics. So we are going to have these hypotheses. Some sort of statement, and we're going to be trying to prove that statement right or prove that statement wrong. And I'll show you how to do that in a bit. We have a long way to go until we get there. But ultimately, that's what we're going to do. But see, our thing is all about probabilities. So here's what the rare event rule says. It says if you start with some assumption, that's your hypothesis. You're going to assume that it's true. And you find the probability of that assumption is really, really small, then your assumption's probably wrong. You with me? So if I start with some assumption like, I'm going to assume that I'm going to be drawing out or sorry, I'm going to assume that the probability of randomly selecting a blonde person from Merced College is like, I don't know, 50%. So I'm going to random select that and see that the random select a person and probability I'm going to get a blonde person is 50%. And I do these experiments over and over and over again. And the probability of selecting a blonde person is actually way different than 50%. Was my assumption right or wrong? Well, I look around the campus. There's lots of brown-haired people around here. There's not a whole lot of blonde people on our campus when I look around. I'm not even blonde anymore. My grandmother said, "Did you dye your hair?" Yesterday. She thought I dyed my hair because it's getting darker. I don't know why, but it's getting darker. Anyway, and then it's eventually going to all fall out, and I'm going to get fat, and that's just life. I just found that some girl said today, "Yeah, when you turn 30, everything goes downhill." I said, "You failed my class right now." That's the good thing I'm only 21, you know. Anyway, I've said that for 10 years now. But anyway, so imagine my proposal here for a second. I go out there and I assume that the probability of selecting a blonde person from Merced College is 50%. Okay, assume that. So 50-50. That's what I'm assuming to be true. Assuming, that's my hypothesis. Then I go out there and actually do some research and start randomly selecting people. I find that I'm not getting 50-50. I'm getting like 10% blonde, 90% brown, black, or red, or whatever. You with me on that? Is that significantly different than my 50%? Is the actuality of blonde people different than my assumption? If it's different enough, then I can assume my assumption is probably wrong. Are you with me on that? So we're using the probability idea to say whether or not your statement is true or false. That's the idea of the rare event rule. It says you start with some assumption, and if the probability of that assumption is really small or really different from what you're assuming, then you can say that your assumption's incorrect. So this is the basis for hypothesis testing. So here's how it's really stated mathematically. I kind of explained it to you in normal English. Here's the math version. If under a given assumption, the probability of an event is really small. I know that's a very mathematical way. If under a given assumption the probability of an event is really small, then that assumption is probably wrong. Let me give you another real-life example of how you can visualize this, okay? Let's say right now that I assume I'm going to walk out that door and get hit by a meteorite. I assume that. I base my life on that fact. So this is the last hour of my life. I'm going to walk out that door and I'm going to die. Gone. I'm actually Superman, so invincible, but I was Superman for Halloween because the glasses kind of works for me. But anyway, that would never happen to me personally. You guys, you're all screwed because meteorites can take out this whole room. But me, I'll be fine. But let's assume I'm going to step out this door and bam, get pounded by a meteorite. That's what I assume. I'm going to assume that that's a true statement, right? What's the probability that's going to happen? Is it high or low? How low? 0.000000000 for a long time, and then maybe like a 1, right? It's pretty low. You with me on that? If you do the research and you actually found out that the probability of me getting hit by a meteorite, considering the physics of this or considering some evidence, right? Some evidence has to be there. Then you'd say, well, the probability is so low that your assumption is probably wrong. You're probably not going to walk out that door and get hit by a meteorite. Do you see the picture? So I'd be living my life on some assumption, or we're going to have a hypothesis we're going to assume to be true, and then the probability of my assumption is probably really, really low. or the evidence suggests that the probability of your event happening is small, then my assumption I'm going to get hit by a meteorite is probably incorrect. Well, then your hypothesis was wrong. That's the corollary. Do you see the connection between those two things? That's the idea of hypothesis testing. Would you like to do one more example to see how it works out?
Yeah.
Thanks, Karina. I'm glad you do. All the rest of you are going to just tag along with me and Karina as we do this example. Are you ready for it? All right. You awake today? Oh boy. What's the average body temperature? There's a band by that name, right? 98 degrees or something. Back streets back. All right. Oh no, that's the next one. Too legit to quit. No, that's not it. Who was 98 degrees then?
Nick
What'd they
Lachey
say?
and his brother.
He had a brother? They made two of them? Okay, body temperatures have an average. What was one of their songs?
I don't know. Nobody knows.
That's sad. They're not even a one-hit wonder. Oh, that's really sad. Body temp has an average of 98.6 degrees and a standard deviation of 0.62 degrees. Let's think about that for a second, all right? Now, when you were a little kid, maybe you still do this now, and you take your temperature and you said, I have a 99 degree, I'm sick, Mommy, I can't go to school. Maybe you still do that now. 99, I'm sick. Does everyone have the same basal body temperature? I used to run cold because I'm a cold-hearted person, but mine is usually around 97, like no kidding, it's like 97.1. That's usually what I am, and I'm fine, I'm normal, I'm not like dying or anything. It's about 1.5 degrees lower than the average body temperature of 98.6, how it's been my whole life. Some of you guys are hotter. You're hot-blooded people. Some of you run at 99 degrees. Anybody run hot? Anybody know? Okay. 99.2. That's and he's fine, right? With 99.2. Because not everybody is the same. I know y'all are told everyone's all the same. No, we're not all the same. We're all built a little bit different. And so your body temperature might not be the same normally as someone else's. You might have a higher metabolism or slower metabolism. It means you're going to run higher or colder. That happens all the time. But the average, the reason why they check it against 98.6 is because in most cases, 98.6 is what people are, or around there. It's a pretty normal distribution, as a matter of fact. And it has a standard deviation of 0.62. So what you know from that is that 68% of the people are going to be plus or minus 0.62 away from that. You with me? Empirical rule, coming back at you. 95% of the people are going to be within 2 standard deviations of that. 99.7 within 3. So it means that not everyone is going to have exactly that same temperature. It's going to range just a little bit around that. Are you still okay? That's what we're talking about. Okay. A sample of 106 people were selected out of any population. Here's the question. What's the probability that that sample will have an average, that the average temperature of that sample will be less than 98.2 degrees? So what's the probability that the average temperature for the sample will be 98.2 98.2 degrees or lower. I don't know. Before we even do this problem, we're going to talk about it for just a little while. Talk about it for just a little while. The first thing, you've got to be able to identify whether you're working with a group or whether you're working with an individual, because you have to know which z-score you're going to calculate. This one or this one. There's only two for right now. There's only two. But you got to know which one is which. That's one of the key things we're learning in this whole section. So let's read through there. Body temperature is an average of 98.6, standard deviation of 0.62, sample of 106 people were selected, find the probability that average temperature for the sample will be 98.2 or lower. That tells you a lot of key information there, right? You just have to kind of interpret it. Because what I'm going to do on your test, I'm going to give you problems like this one and like this one. The original questions those came from last time, right next to each other. I mean, they're going to be right there. And one of them's going to use this, and one of them's going to be that, and they're not going to be the same. Are you with me? You sure? Okay. So, question. When I'm dealing with that problem, am I looking up the probability for an individual or for a group of people? Individual or a group of people? What do you think? If it was an individual, it would say, find the probability that a randomly selected person, or one item. Here, this is saying a couple keywords for you that clue you into a few things. Clue you in on which formula to use. First thing it says is a sample of a certain number of items. A sample of 106 items. There's got to be somewhere where you're going to plug in that 106 items. If you look up here, this is for an individual. Sure, it's got a mu. Sure, it's got a sigma, the mean and the standard deviation. But the x, is x an average or a data value? You need to know that that's a data value. Is x an average or a data value? Definitely a data value. Okay. There'd be no place to put your n. There's no sample size there. Also, one more keyword. What's the probability that does it say, what's the probability that the temperature of, no, it says the, what now? Average. That's a key word. You've got to find some place where you're going to plug in the 106 and it's dealing with an average. If you look back up here, compare these again, this is the data value. That's not standing for an average. This would be like, find the probability that a randomly selected person has a temperature of less than. That would be the temperature. Here though, what's that stand for? The average of the sample. What are we dealing with over here? The average of the sample. That clues you in on which one to use. Over here, this stands for sample size. What's our sample size here? Okay, so that's relevant for our case. So n is 106. So again, are we dealing with an individual value or dealing with a group here? Definitely a group. Keywords, sample of a certain number of people, that's key. Also, the average thing. The average clues you into, we're using this z-score. Oh, what else do we want to find? Oh, can you find this? This, and that, and the other. Three things you got to find. A couple of them might be kind of confusing to you, because when you think about it, here's kind of another piece of information you know. There's actually two averages going on. Do you see it? There's two averages. That's the average of the, wait a minute, population or sample? Sample. This is the average of the, okay, so that you need to distinguish between those two things. So when we read our problem, yeah, n's pretty easy. N's the sample size. So here we have 106 people being found. What is the mu and what is the x bar? What's the mu? The mu should be the population. What is that one? 98.2 or 98.6? Okay. The 98.6, that's for everybody, right? That says body temperature has an average of. That means that everything, that's the whole population. So yeah, this one's going to be 98.6. What's x bar then? 98.2. Good. Hey, x bar is what you're questioning. Okay, it's always going to be based with your sample. It should be like, find the probability that the sample will be blank. That's your x bar. That the sample will be 90, that the average of the sample, that's the average of the sample. 98.2. Sigma, there's only one of those. So sigma's generally not too bad. How much is our sigma here? Okay. Okay, so we've read through our problem real carefully. We've distinguished that we are going to be using our z-score for a group of individuals dealing with an average of a sample. It's clearly stated in some of the keywords that we have in our problem. What's the next thing that you should be doing here right now, folks? Say it louder. Let's find a z-score. Because what we want to do, translate this distribution into something we can work with, a standard normal distribution. The only thing that does that is our z-score. So we're going to be using z-score. Before you do it though, stop. You're all doing something right now that you probably should think about before you get started. You need to check to see if the conditions are met to use this information. You better check that. Better check conditions. Conditions, there was a magic number there. There's also a statement if you didn't match that magic number. If you didn't match either of them, well, then you couldn't do this. So the first magic number is how much, everyone?
30.
Good, 30. If n was greater than 30, did we have a problem whatsoever? Didn't matter what we said or anything else, we could use it. So how much is our n? Is that bigger than 30?
Yes.
So can we use this stuff? But wait a second, wait a second. I didn't say anything about being normally distributed. Do I have to have that statement if my n is bigger than 30? Read through your conditions. Read through your conditions again if you don't know. Should be on your previous page. Okay, so do I need the statement, the population is normally distributed, if my n is bigger than 30? No, it was a very amazing theorem, the simple limit theorem, said that no matter what your population looks like, this thing could be completely skewed one way. It doesn't even matter. If you're taking sample sizes bigger than 30, your sampling distribution for the mean will be normally distributed, and therefore you can use the standard normal distribution. You can use a z-score if your n is bigger than 30. Now let's do a little experiment. Watch on the board here, please. Let's say that I didn't have 106. Let's say it was now 10. Let's say it was 10. Could I use a z-score here? What would I have to have in my question in order to use a z-score here? That's the one. So you have to have one of two, well, you have to definitely have n bigger than 30 or n less than 30, but the normal distribution part of it. Okay, so that's your conditions. If you have neither of those things, then you can't do it. Okay, back to 106. I want you all to work on your own. Find me a z-score, please. If you've already done that while I was rambling on about all this stuff, draw the picture. If you've already done that while I was rambling on, find the area. If you've already done that, oh shoot, all right then, make the interpretation. Are you guys enjoying this stuff yet?
Sure.
I hope so. It's going to get more interesting. Like it's not already, I know, right? Crazy. How can it get more interesting than this? It's like the best ever. This would be just about as interesting as if the Colts were to play the Dolphins. Yeah. That'd be crazy. Who wants to lose more? Well, the first thing you need to do, make sure you're setting up the formula correctly. I would like you to label these things before you get started. That way you know where everything's doing. Don't just do this off the top of your head. Otherwise, you might screw up the averages. I don't want that to happen. You might mess something up as far as sample size. I don't want that to happen. There's lots of numbers that are going to be floating around at you. Label them. That way you can go directly from these values to this formula. No problem. What is our X bar here?
90.
We've already done the legwork and identified that, haven't we? So now we just have to substitute that in. 98.2. Okay. Minus. We take our X bar minus our mu. What's our mu?
98.6.
Notice how if you get those two things confused, you're going to get a positive z-score where you want a negative z-score. Or a negative z-score where you want a positive. It'll be off by a sign. It'll be the opposite of what you're looking for. Your area will be completely wrong. Okay, over, what's the next thing I put?
0.62.
Divided by what now?
Square root of 106.
The square root of, not just 106, right? That'd be way off. But the square root of 106. Also, you need to try not to round as much as possible. The rounding really will affect these problems, especially considering z-score is accurate to 2 to 3 decimal places in some cases. So if you're rounding to 2 decimal places, then your answer, your z-score is going to be off. You need to at least have like 3 to 4 decimal places after this square root of 106. So don't just give me 10. The square root of 106 isn't 10. It's 10 point something, but it's not just 10. So you can't start rounding that stuff. Are you with me? Otherwise you are going to be off. Especially when you're dealing with like these decimals like 0.2, 0.6. It's pretty important to not do that. So our z-score, we've got, looks like negative 0.4 to me, over something, 0.62 divided, what's the square root of 106? 10 point, what was it? 29. I'm going to put 2956. I just want to be sure that I'm not rounding too much. Just it's better safe than sorry. I don't even want to be off by a little bit. So negative 0.4, I'm going to leave that for a second while I calculate this. Notice I did the top portion of my numerator, and I'm now working on my denominator. I have to do the square root first, find out what the number is, then do our division here, find out what that number is, and then we'll be able to do our final division. What is 0.62 divided by 10.2956?
0.06022.
Repeat that one more time.
0.06022.
Perfect. And now we'll do this division. We'll do negative 0.4 divided by 0.06022. You're dealing with very small numbers, aren't you? If you rounded here inappropriately, this is going to be way off. Well, our z-score's certainly negative. Certainly negative. Okay, how much is that z-score?
6.6.
Wait, what now?
I got
6.64? 6.64? Raise your hand if you feel okay getting the z-score of negative 6.64. Okay, let's draw our picture now. I'm going to move over here. I used to be so good at those. There we go. What's in the middle?
0.
Where's negative 6.64? Right or left? How far left? Way left. Way in the left field. It's like here, actually. But we'll put it over here. It doesn't have to be exactly the scale. Z equals negative 6.64. Now you've got to shade your picture appropriately. So let's look at our question again. Are we trying to look for the area to the right or to the left? Read it carefully. Blah, 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 blah. 98.2 or lower. Look at here is the z-score for 98.2. That's the marker. Now you're going to try to figure out where's lower, to the right or to the left. So we're looking for this area right there. What are you going to look up on your table? what would you try to look up on your table? Negative. Now, if you look at, can I borrow that? If you look at your table, is yours broken or something? Oh, there we go. Broke your table. If you look at your negative z-scores, it stops at negative 3.5, and it says something down there. It says for any z-score outside of negative 3.5, you're going to use what value? I hope it says that, right there. Negative 3.5 and lower, use 0.0001. For us, that's not even going to be very accurate, but you're going to use it to signify that the area is actually not 0. There is some chance that that's going to happen. Is it very likely? By the way, if I find this area is 0.0001 like it is, do I need to subtract 1 from that for this case? No, it's giving me the area to the left, and that's what I'm looking for. So this probability is 0.0001. Someone with a calculator, look it up on your calculator. So this was from your table, you got 0.0001. How about a calculator?
It's 10 zeros and then 157.
You plugged in negative 10 to negative 6 point, how many zeros?
Negative, or 10 of them left to the decimal. Or right to the decimal. 10 of them.
Like that?
577 at the end. 1577. There you go.
Okay. Is that a large probability? By the way, this is how inaccurate that table is for this information. This is like a billion times bigger than that. So just so you know, your table after the 3, not that accurate. Within the 3, it's relatively accurate. But here, 0.00, 10 zeros, and then is that probability large or small? Very small. So here's the point. If you went out there and said, I'm going to assume that the average temperature for people is 98.2. I think everyone's wrong, and people actually run colder than normal, 98.2 degrees. And you did this, and you selected 106 randomly selected people, okay? You found their average. The probability of you getting that average temperature of 98.2 or lower is that. Is that probability big or small? What dictates big or small for you right now? 0.05. Remember the rareness? 0.05. It's less than that for you right now. That's rare. That would be rare. This would be very, very unusual. Standard deviation of -6. I mean, my gosh. I'm sorry, not standard deviation of -6. Negative 6.6 standard deviations away from the average is what you just calculated using the z-score stuff. Pretty darn rare. Why is it so rare? Look at your sample size. How many people are you selecting? How many? That's a lot of people, right? That's a large sample size. So yeah, maybe some of them are going to be less than 98.2. I am, but you're not. And probably you guys aren't. You know, you're going to be right around 98.6 or higher than that. So averaged out together, if there's 106 of us, it's going to be really, really close to this. And if it's not, it's really rare that it's not. That's what you're showing here, is you're trying to find the average of the whole grouping of people, their average being greater than or less than a certain number. By the way, if we change this, if we made it like 98.4, if we made it 98.4, would this probability go up or down? Up or down? 98.4. We'd have -0.2. Probability goes up or down. What do you think? Z-score goes up, so probability goes up for this case. We have a greater probability that happened. You could ask many different examples too. What's the probability of greater than 98.2? If you did that, if I asked for greater than 98.2, which side do you shade now? You'd have really darn close to almost 100% of the people are going to be greater than 98.2 as an average, not an individual, but an average. How many people feel okay with this? So we made a transition from looking at individuals to looking at samples and averages of samples. That's our transition. Do you feel okay with the chapter 6 stuff that we've just covered? So at this point, I expect a few things from you. First, I expect you to be rock solid on looking up z-scores and finding probabilities, and looking up probabilities and giving me z-scores and values, going forwards or backwards with that table that you have. Using your calculator if you need to, that's fine. I also expect you to be rock solid on distinguishing between a z-score for an individual and a z-score for a group, like we've been practicing here. You gotta be really good at that, because you're gonna have information right next to each other. One question you do one way, another question you do a different way. Even if it has the same numbers, you'd be doing it a different way, based on the question, yeah.
Just a question, like when it comes to our homework or doing any work, would you, if that were a possibility of that being our answer, would you rather have the answer from the calculator or from our table?
It doesn't matter, I check both.
Okay.
If you're gonna do one or the other, just say this is from the table. On your test, tell me if it's from the table or from the calculator. Say, I am using a calculator. I'm like, okay. If you're using the table, then no problem.
But you want us to write it out like that, even though it's because the calculator gives it to us in a scientific notation?
Write it out. Because I'll have a lot of people giving me this. The probability is 1.6. Yay! No, that's 160% probability. And then you're gonna be that. No, don't do that. If you're gonna do 1.6 times 10 to the negative 10th in this case, or something, whatever that is, 11. Move it over. Good question. Any other questions? Those are great questions. Thank you for those. Anything? Otra? Anything else? You sure? You sure? You sure? Now, we are going to start something else here.